Hello everyone. Today our group will present chapter 7, which is the best spherilene technology for LLDPE and HDPE production. My name is Elvaron Evaristus and my partner name is Evanson Ong. The spherilene technology is a swing process that has been designed to allow the production of a flexible, high-quality product grade slate including high-density polyethylene HDPE, medium-density polyethylene MDPE, linear low-density polyethylene LLDPE, and very low-density polyethylene VLDPE. The process consists of a polymerization unit with two gas-phase fluidized bed polymerization reactors in series, in which ethylene and comonomers such as butane-1 are converted to various types of polymers. Downstream of the reaction section is a product finishing section, additivation, and extrusion. For the linear polyethylene, the family of linear polyethylene includes high-density PE, HDPE, high-density high molecular weight PE, HMWPE, and then ultra-high molecular weight PE, UHMWPE, and then low-density PE, LLDPE, and last is very low-density PE, which is VLDPE. So basically, all of these are produced using low-pressure technologies, and because the comonomer content is the only factor influencing the crystallinity level, unlike traditional high-pressure LDPE, along the molecular backbone, the comonomer is grafted to form short side chain branch that disturb the macromolecules' capacity to pack and consequently form crystals. This means that the polymer density decreases as the monomer content increases. The high pressure process produces LDPE with both short and long chain branch. The density level is influenced by change in process parameter like temperature and pressure, and the polymer is made up solely of ethylene monomers units, which is homopolymer. Copolymerization occurs in linear PES through the introduction of olefins that transition from propylene to octane. The polymer properties vary based on comonomer type and amount. Generally, some properties improve with an increase in the short branch length passing from propylene to butene to hexane to 2-methyl-1-pentane to octane. Next, this is the chemical reaction. Addition polymers are made from monomers that contain a carbon-to-carbon double bond. These carbon-to-carbons are reactive and responsible for connecting monomers together to produce a polymer. For example, multiple ethane monomers undergo polymerization to produce polyethylene. Next is high-density PE, HDPE, the oldest member among linear polyethylenes, with commercial production starting in 1956. By convention, HDPE density range from 0.940 to 0.970 gram per cc. The corresponding crystallinity level is between 60 and 80%, and the melting temperature is from 130 to 135 Celsius. Polymer with density in the range 0.926 to 0.940 G per cc are classified as medium density PES. And high density, high molecular weight PE, which is HDWPE, characterized by a higher MW than the traditional HDPEs. Commercial grades are mainly copolymers containing small quantities of comonomers having a density range between 0.944 and 0.955 G per cc.
Okay, linear polyethylene for ultra high molecular weight PE, HDPE. HDPE is a line polyethylene with short side chain which are able to reduce its density to 0.925 gram or cc or less. Among linear polyethylenes, LLDPE is the youngest member with consistent commercial presence since 1980. Today it represents about the 23% of the total polyethylene consumption. And then the linear low density polyethylene, LLDPE, is a linear polyethylene with short side chains which are able to reduce its density to 0.925 gram or cc or less. Among linear polyethylenes, LLDPE is the youngest member with consistent commercial presence since 1980. Today it represents about the 23% of the total polyethylene consumption. And the last one is very low density polyethylene. That is VLDPE or ULDPE, very low density polyethylene. These linear polymers of ethylene shows a density that is lower than 0.915 gram or cc. Commercially available VLDPE grades typically range from 0.880 to 0.910 gram or cc and include ultra low density polyethylene. For the process flow diagram, ethylenes for LLDPE, comonomers like butene or hexene are added. Catalysts such as ziglenata are introduced to initiate and control the polymerization reaction. The comonomers, ethylene and catalyst are mixed in the first reactor, then going to low pressure vessel 1. At the same time, we go back to a first reactor. The polymerization of ethylene and comonomers is an exothermic reaction, meaning it releases a large amount of heat as ethylene molecules link together to form polymer chains. This process is being cooled in the cooler 1, going to heat exchanger 1 to remove excess heat. This helps keeps reaction conditions stable and for achieving consistent polymer quality. Before going to lock hopper, the unreacted ethylene and comonomers are being recycled back to compressor 1, then go to the cooler and heat exchanger to cool down, then back to the first reactor. After that, in the lock hopper, a lock hopper is used to manage the transfer of solid polymer particles like polyethylene fluff between different pressure zones. This system is particularly important for maintaining pressure control and ensuring a continuous flow of materials. Then it's going to the second reactor. In the second reactor, it's pretty much the same process as the first reactor, but after the polymer undergoes low pressure vessel 2, it's going to steaming section column. In there, steam is introduced to facilitate the condensation of volatiles. This helps in removing residual monomers and byproducts from the polymer particles. The steaming section columns help in separating unreacted monomers, solvent and other volatile components from the polymer product. Before going to drying section, column heat from the hot polymer or gas streams is being recycled and dry all the way to compressor 2, then cooler 2 and heat exchanger 2, go back to the second reactor. Polymer is then discharged to a proprietary unit for final monomer stripping and catalyst deactivation in the spherical product particles. A countercurrent steam flow completely strips off hydrocarbons from the polymer, which are recovered, dried and recycled to the reaction. The wet polymer coming from the steaming section is finally dried by nitrogen in a closed loop system. The polymer is transported to the additivation and extrusion section, where stabilizers are added and the polymer can be extruded to pellets. This is the final products for the process flow, that is pellets polyethylene. In conclusion, the spherilene process is a highly efficient and versatile method for production advanced polyolefin polymers, utilizing two-stage gas-phase polymerization to create materials with customizable properties. By precisely controlling catalyst activation, monomers composition and reaction condition in each reactor stage, the process enables steroid polymer characteristics such as monomer molecules, molecular weight, distribution, density, and copolymer formation, efficient recycling of monomers, gases, and careful catalyst deactivation, and polymer drying contribute to environmental sustainability and cost effectiveness. The final additivation and extrusion steps ensure the polymer is stable and readily usable in various applications, making the spherilene process a valuable solution in the field of polymer manufacturing. That's all from us. Thank you.